Okay. Okay, thank you. I'm Gavin. I'm going to start with my acknowledgments. So I want to thank DARPA for funding the work that I'm going to talk about today, and thank Paolo and everyone for inviting me to talk. So it occurred to me, first thing, normally when you come from industry, you have a lovely slide that demonstrates how excellent your company is. And I didn't do that, so I completely forgot that that's the norm. So I'll just tell you about the company I'm coming from. So Scientific Systems is a small business based out of Boston area, about 110 people, but been around for over 30 years doing research for the Department of Defense. Generally, I would say kind of the goals of the company are kind of multi-agent autonomy and AI-enabled autonomy in general. So that's kind of maybe the very quick overview of the company. If you have more questions, feel free to come talk to me. But today, what I want to talk about is uncertainty's role in metacognition. And I've really liked a lot of the talks. It really kind of feeds into some of the ideas that I wanted to present. And one of the main assumptions that a lot of methods, when you start talking about closing the loop in lifelong learning or continual learning, you have this hidden assumption in there that says, I know whether I'm confident or my certainty about something, and I need that piece so I can then figure out what I want to do about it. And we all know softmax has its confidence, right? But it's not really uncertainty. We all know it can be tricked. It doesn't give you kind of necessarily a reliable measure, but we do it anyway because it's easy and this is potentially a hard problem. So I want to help with maybe a way to bring up a little bit of your uncertainty quantification. It's going to feed into another talk you've heard already. But maybe we can attack kind of this fundamental component that I believe we really need to close this loop well and kind of reliably. So there's been a lot of, I'm not sure I knew what the definition really of metacognition is, so I went ahead and started with the way I kind of think about it. So I borrowed this plot from perceptual autonomy, which was kind of originally for how does a classifier work in terms of classifying things. And I want to kind of use the verbiage, but amend it to think more at like a decision-making level. So first off, we're going to start with kind of in the bottom corner of unknown unknowns. So think of it as like the system encounters something that it hasn't seen before, it doesn't know what it is, and it doesn't know what to do with it. So what the axes I really want you to think about are things that I can recognize and know what they are versus things that I know how to respond to. So in this case, one of the quadrants doesn't make a lot of sense. The unknown knowns, meaning you know how to respond to something, but you don't know what it is. That's maybe not a very good box to be living in. That'd be a little strange. So the way I think about it is a agent or policy, think of it however you will, decision-making system, ideally is operating in known knowns. It knows what it's looking at and it knows how to respond well. So that's typically how we train these things. Could be supervised training, could be reinforcement learning. That's kind of typically what our goal is when we go deploy these things. But oftentimes, as people have talked about, you send it out into the real world, it encounters domain shift or new objects or things, and it kind of falls flat. So I'm going to classify those as metacognitive systems would be able to get from these unknown unknowns in the environment. So it's still detection. So let's ignore the scenario where you don't detect something at all if you have a classifier, but it's uncertain about what this thing is, and therefore it also is kind of uncertain what to do with it. So I detect there's this thing over there. I don't know it's a trash can, and I don't know if it's trying to do me harm for some reason. So this is kind of the goal of where we want to get to, is if we can close this loop of we've trained it to do something that we want it to do, and we put it in a scenario that's not necessarily totally new. It could be, but still representative. It's going to determine when it's not sure about something and take action to then figure out how to respond to it as it operates in time. So the goal here is to close the loop between uncertainty and continual learning as these systems work in the real world so they can even improve themselves. So that's kind of the way a lot of this is going to be framed. So today I'm pretty much just going to focus on the first step here, which is getting from unknown unknowns to known unknowns, meaning I now recognize that there's something that is new in my world, but I don't really know what to do about it. So I'm going to defer to the crowd on if I can tell you I found something new, what do I do? If you have a lifelong learning technique, come talk to me, we'll close the loop, life will be great. But the kind of trick here is, a lot of systems that are being deployed right now don't have this measure. So in classification, again, we talk about softmax. In regression, sometimes there's just nothing. I mean, it just outputs, you're here in the world, whatever it may be. So these are kind of hard to come by with the way things are deployed now. So the problem we wanted to attack under this DARPA program was, what can you do if you have some existing model that you spent a lot of money and time training and it performs relatively well in these situations, but you want to add the ability to represent kind of a more accurate uncertainty to it. So obviously retraining evidential learning was a good example of a way if you wanted to train from scratch a model, you could add an uncertainty head to it and then go from there. But this is really kind of what we're assuming, and this plays well into the large language model. There's been several people talk about they don't have compute to train these things from scratch. We also do not, so we sympathize with you on that front. But we see a lot of things kind of out there in the world now that look kind of like this left figure. So our use case is in autonomous driving as well. So maybe, there's, for some reason, the environment, you have a misclassification. It thinks a car is a person, and it has very high confidence about it. That's kind of one, traditional failure that people have seen. Another one we see a lot is regression tasks related to pose of a vehicle or things like that, where it just gives you a value. So you have no notion of, how certain is this? It just gives it to you, and you either blindly trust it or I don't know what the alternative is. So what we really want to do is get to kind of more on the right. So one is, in the classification case, we don't just want a confidence. We want something that's kind of has to do with the way this model is trained and the environment it's in. So we want something that works under these domain shifts and things that occur to it. And in regression, we really need these uncertainty bounds. They could be Gaussian, non-Gaussian, depends on what you want to do. Now, today I'm going to talk mostly about kind of a Gaussian case, and despite the fact that I'm going to tell you that it doesn't depend on being Gaussian, but part of the reason is DARPA was interested in if I have data that's processed through a neural network, could be images or LiDAR or something like that that's traditionally not directly used. And then I have a more traditional sensor like an IMU or something like that that typically has kind of a static covariance. How do I combine these in a statistical filter? So typically to do that, if you're in the Kalman world or something like that, you need to have nice Gaussian. So the question is, in these processed neural networks, what we really want is the output uncertainty so we could fuse them together. So that was kind of the overall goal. So there's a couple pieces here. So I kind of talked about generally the goals of what this program is. We looked at the KITTI data set. So for probably many people are familiar with this one, but it's an autonomous driving car data set where they put all of the LiDAR camera, GPS, about every sensor you could possibly want, and drove around in a large number of scenarios to give a fairly diverse data set. And that's kind of what we use as our real world data set. One of the challenges I'll get into is this would be a really easy problem if we knew what our prediction error distribution was. So normally in the real world, you don't have that, right? You have, just whatever your data that you can measure is. So I'll talk about a couple of examples of ways of potentially dealing with that. I also apologize. We kind of named this thing automatic. So anything you see in automatic, think our use case, not the literal sense of the word, and I don't remember what that acronym stands for, so it was something very convoluted, but worked out nicely to that name. So understand that one. But the way kind of structurally it works is, we have some process data, LiDAR camera, we have some pre-trained ML models, typically there's a couple here, DeepVO, these visual odometry or LiDAR odometry type networks, typically kind of a CNN with a recursive part to it. Then we're going to add kind of a piece to it, this meta model, which I'll get into. And one of the nice things about this is we get to choose what our representation of uncertainty is here. So when I say uncertainty, you could think, Gaussian here if you like. And then, kind of the goals here, you combine it with a traditional IMU or something like that. So structurally, this isn't going to depend on, now part of the reason, you see maybe the feedback particle filter here, that's where we're getting around, this Gaussian assumption of using a Kalman filter or things like that. So if you wanted to choose a non-Gaussian representation for, whatever reason, sometimes it's not a good measure. There is a way that you can kind of do all of this under that non-Gaussian relaxation. So meta-modeling. A group out of MIT was kind of the original publishers of this idea. And it basically looks at the intermediate outputs between the network. So rather than just looking at input-output relationships to try and quantify uncertainty after the fact, with your base network, we're going to not change anything about the network, but we're just going to look at what these intermediate layer outputs are. So the idea being the distribution of those outputs gives us much more rich, information to try and determine whether this is, to kind of fit our distribution to, basically. So this is going to be fairly important that what this allows us to do is when you have state-dependent noise, trying to separate that just from input-output relationships is very hard to do. So this gives us a bit more information into the neural network. Now, granted, a lot of this work, I will admit, we did on kind of deep networks, but not LLMs. So we are interested in extending this to LLMs, but this does assume that you are able to get kind of these intermediate access to these outputs. So you don't have to tell me the weights of the network. You don't have to say, what was the original training data, but it does need that to train this network. So the structure of, a meta model in this case is you start with kind of these small linear type of networks that are really like, think of them like encoders. So you're getting to some lower dimensional feature space. Typically some of these layers may have a huge number of features, so you kind of want to reduce down that space. So from that, you get all of these kind of layers encoded into the same latent space that you can then bring together and tell you parameters about some distribution. So this is what you're choosing. So if you look at the example here, this was a classification task, and it's looking at a Dirichlet network, Dirichlet distribution to say, if it's very sharp, then this is probably a good classification. If it's, kind of blurred, then maybe that's not the case. So this was aimed at telling you out of distribution samples. So you can train these things to tell you a variety of things as long as you can represent it as a distribution. That's kind of the key to it. So this is a little bit faster, quite a bit faster actually, depending on how big your network is, because these are very small networks, so these are single layer, maybe a couple layers. So you can do this kind of after the fact without messing with, potentially your base network that you spent lots of time and money training. So this is great. Now we have kind of a way, as long as you have a distribution representation of what you want to know, there's now a way you can even use your own data. You don't have to use the original training data from the base network to kind of add uncertainty onto this base network. So if we look at a pretty simple example, the first thing we tried was a made-up kind of thermistor. You have resistance. You have some logarithmic relationship to temperature based on the Steinhart-Hart equations. But this allowed us to kind of inject noise in different ways and look at, how well are we able to capture this. So one of the things you heard in a talk yesterday was the different types of uncertainty that exist. So aleatoric is typically your data related uncertainty that you cannot reduce, so getting more training data does not help you in that case. Epistemic is related to your model, could be outside of your distribution. In this case, I'm actually going to talk about a component of epistemic that is randomness in your network. So kind of one of the key things is if you can separate these two types of uncertainty, there are some interesting things you can do with that information. So if you know, for example, your epistemic uncertainty is high, it may tell you you should collect some more data or work on your network structure to improve that process. If you know that that's relatively low, your aleatoric is maybe higher than you want, and the question of what do you do with your millions of dollars or $1 million, don't go buy more data because it's not going to do anything for you. So being able to separate those is kind of a nice property to have. And those break down even further into whether they're state dependent or not. So homoscedastic is a lovely made-up word that was relatively new to me a couple years ago. That's just state-independent noise. So it's additive, basically in the way we did it here. Contrasting to heteroscedastic uncertainty, which is state-dependent noise, which is now much harder to deal with. So as you can imagine, a lot of times the state-independent noise, you could pick that up with input-output relationships. So as long as it's you have enough data, you could probably do this technique without really using a lot of the intermediate layers and get that. Now, the heteroscedastic, that is very hard. The results were awful when we tried to do that with just kind of the input-output relationship. Add this on. The last piece is, so those are, imagine a deterministic network. In the definition that we're using, the variance of your mean in a deterministic network is going to be 0 in this case. So I'll show you plots that say epistemic uncertainty is 0. Okay, well, it's 0 in the sense that by definition here, there's no randomness in it. So in kind of the last case I'll show, we add some stochastic elements, think of Bayes nets into it to kind of make sure it can separate it. Now granted, in practice, you probably mostly care about the prediction uncertainty, which is just the sum of those two, if you were going to use this downstream. So in the first case on the left, we added kind of just simple Gaussian noise, and you can see that sure enough, we're able to realize, yes, there's no randomness in this model. Therefore, our prediction uncertainty is just our aleatoric uncertainty in this case, and it was able to detect very well just a single variance that was added to this model. On the second case, now we add some state-dependent noise, and you can see you start to get a much more interesting behavior here. So this is really following just from the type of function that we were adding this to. But we're seeing it's able to capture this quite well, regardless of the type of noise and how it's coming into the system. So extending further, so what happens if we have some randomness? So you can think of ensembles, you could think of any sort of randomness in your network. What you want to do in that case typically is extract out your epistemic uncertainty. This is the part you could really do something about. So in this case, it would tell you, hey, maybe I should collect some more data down here at these low resistances, for example. And we still get a nice prediction for the aleatoric uncertainty, which was still constant in this case. Compared to the deterministic, we're still looking good in terms of how those are able to detect. And then if you were going to use this in real life, for kind of overall uncertainty of that prediction, this is the piece you want. So this is what it would look like. So it gives you a way of getting the information you need to kind of close that loop. This was another example here. We actually did this with dropout at inference time, so we weren't using ensembles, but the concept is still the same. So another thing we wanted to study is, okay, it's good, it captures different ways, different types of uncertainty, different dependencies. How sensitive is it to the network architecture? So what I'm kind of showing here, we tested against networks that were maybe wider and kind of shallower versus maybe narrower and deeper, and it had very little sensitivity to structure or the shape of the network itself. And part of this is, these networks, these meta networks were really trained on every single layer. So I'll get into, is that a smart idea? But if you basically think about, you're seeing how, these predictions are basically propagating through, and that's what's providing this information. It doesn't really matter. So this works regardless of, you could have linear layers, you could have convolutional layers. It's not really dependent on what type of layer you have. So those were nice. That's kind of looking at, a very simple scenario. So the kind of next step was going to the KITTI data set. So in this case, we were taking LiDAR and IMU. So on the left here, we show, if you just kind of use IMU, as you might expect, it wasn't a super high quality IMU, so it drifts all over the place. And this would be kind of painful if this is what your car was really doing, your autonomous car was doing. You've probably run through somebody's house at this point. So what we want to do is bring in LiDAR. So, the controls community would say, basically we're going to take all of our data set, we're going to fit a static covariance to it, and we're just going to use that and Kalman filter. And that's kind of the traditional, sensor fusion approach to this, which, it does a lot better. So we'll say, that does a lot better, but there's still pretty significant drift, which to be expected here. There's no position. We're basically looking at position, and we don't have a position sensor. We're not using GPS. So just so it's clear for everyone, we do expect position to drift in this case because we don't have an update. But still, although the shape looks nice, it doesn't feel very satisfying if I was going to try and drive that again. So the question is, in this Kalman filtering, now if we take the meta-modeling at a sample-wise measurement as our uncertainty, we get something that looks much more like this. So the benefit here is we're not looking at kind of the uncertainty of the distribution as a whole, which isn't going to capture this state-dependent uncertainty, which we have. So what the meta-model gives us is by taking your base network as your prediction, your meta-model for your uncertainty, and then filtering it in to the IMU, you have a much more accurate uncertainty measurement per sample, which is why we're seeing still drift, but much better aligned than it was before. So we ended up with around 10–11% average trajectory error improvement. So I want to talk about. This is certainly not story over. One of the biggest challenges here is how do you choose these layers, right? You tell me you have a very deep network. What layers will give you relevant information? Maybe the most naive thing to do is just train on every single one and don't worry about it. For large models, it a little bit defeats the argument of that this is going to be more efficient. You could probably have put in an uncertainty head and retrained from the beginning. So one of the things we're working on now are kind of a principled way of choosing these layers. So you could heuristically go in and say, I'm going to take the end of, maybe I have a few convolutional layers together, so maybe I'll look at the end of that. Maybe I'll grab, the final two linear layers, but that's going to be very task dependent, very network dependent, which is not, really what we're looking for. So one of the ideas that we're exploring now is, okay, so let's assume that I'm going to train a meta model on every single layer, which I know I just said don't do, but let's start there. Then you can use a pruning operation, which is going to basically prune at this the kind of small networks at the beginning at that level, not individual weights or things like that. So it's basically going to, from a norm perspective, say which of these layers is contributing the most to my uncertainty quantification. So, of course, you're going to see a drop in your prediction accuracy when you do that. So we can use a technique from optimal transport to then fuse kind of that large meta model, which is doing a better job, into this much more computationally efficient version, and kind of bring that accuracy back up. I mean, we don't expect to recover everything, but a significant portion. And there's kind of a trade-off between, of course, as you prune, your performance falls off, and there's only so much you're going to be able to recover. So we're looking for kind of the sweet spot in that area. So that's kind of one of the challenges we're working on now. And another one is, I say you can train these to do about anything that's represented as a distribution, but we still have this problem of we don't actually have the ground truth distribution we want to train against normally. So the Gaussian case is nice because we can do a maximum likelihood formulation, and we don't actually need our true ground truth error distribution to compare against. But that's fairly specific. I mean, in an ideal world, we would like to have a distribution to compare against because we have lots of tools to do that, right? We have KL divergence, we have all the Wasserstein metrics, we have a lot of ways to compare distributions, construct loss, and then make those things come together. So as I've discussed with people, if you have a brilliant idea on how to come up with these ground truth error distributions, I'm very interested in that. Please come talk to me if that's the case. But that still remains kind of one of the key challenges, is if we could find clever ways to do this, then we could give you almost any type of uncertainty that you want to know, that feeds into how you would use that, whether it's decision making or whatever the kind of follow-on task may be. This is still obviously work in progress, but we think it shows potentially a lot of promise for these larger models where somebody's going to spend a huge amount of resources training something that works well, and you have far less resources to try and get. Hopefully also in the future people will just train these models with a better representation of uncertainty, and that can kind of come with it. But until then, hopefully this is something that will help us out. And I think I am actually under, so there should be time for some questions.